We have seen a video on SN2 reactions, and you're supposed to see that video before this one. And this is SN1, that is again a substitution nucleophilic reaction, and this is called as unimolecular reaction. And we have seen that SN2 was a one-step reaction, and this is a two-step reaction. Again, we'll see in short what is the meaning of this word nucleophile here. Nucleophile means something which is having negative charge over it, and it is attracted towards this you can say positive charge or nucleus, because it is nucleus loving, nucleophile. So it will search that positive charge somewhere, and you can have species like OH negative, CN negative, something which is having that extra pair of electrons or it, or a negative charge on it. We'll consider an example to understand the mechanism of SN1 reaction. This reaction also takes place in some solvent, and we'll talk about the solvents after this. I have this tertiary alkyl halide here, and reacts with OH negative, which is obtained from say KOH or NaOH, and you get this alcohol by this substitution reaction. And this mechanism, there are going to be two steps. The first step is called as the formation of carbocation. This is the most important one, the formation of carbocation, and let's see how the carbocation is formed. This is our first step, where this tertiary alkyl halide is converted in these two ions, we can say. This, as we have seen in SN2 reactions also, this C2X or C2Br bond here is a polar bond. This Br, being more electronegative, attracts this shared pair towards it slightly. So you can say a small negative charge over it and a small positive charge. And in presence of a solvent, these two ionize or dissociate as this thing, and here this Br negative completely. This Br is taking this electron towards it, and because of that this carbon has lost this electron of it to this Br here. This electron it has lost to this Br, therefore this carbon is now positively charged, and we call this type of species as a carbocation. Like here, this carbocation, is a positively charged ion, and since it is on present on carbon, we call it carbocation. This is your first step. This is called as the formation of carbocation. In the second step, let's consider this carbocation here, and you have these nucleophiles present all over the solution. All over, there are many of them, and you can easily imagine what is going to happen in a step number 2. So this is our second step, and here this nucleophile can approach our carbon, which is positively charged, from either of the side, either from this side or this side, and you can get two types of product, you can say. I'll just show you the products. Yeah, like this. Yeah, if the OH is approaching from left side, you're going to get this product, and if it's approaching from right side, you're going to get this product. And if you heard about optical activity, generally from SN1 reactions you get both D type as well as L type products. So it's effectively a racemic mixture, so it's a mixture of both, 50-50%. So you get 50% this and 50% the other one also. On the contrary, we have seen in SN2 reactions, you have inversion of configuration. The structure completely inverts. Here, you can have, like, this structure is retention of configuration, and this is the inversion. So retention as well as inversion, both the things happen here. See, this was our original structure, and these three CH3 are in the left hand side, and if the product retains it, then it's going to be a retention, and if it inverts, then it is going to be an inversion, and both of them are happening over here. So you get a 50-50% mixture of both of these two types of products. Now we'll see on what factor the rate of SN1 reaction depend. As this is a two-step reaction and the first step involves the formation of a carbocation, therefore this is very important. In fact, the structure of the reactant, whether it is primary, secondary, or tertiary alkyl halide, is important. Consider this thing here. You have these two carbocation, and when this carbon is having this positive charge, it is stripped of its electron and it has become unstable. And these three electron donating group, you call these alkyl groups, they are the electron donating group, and they can easily shift their electron cloud slightly towards this carbon, neutralizing the effect, this positive effect. So this carbon is now stable. You can say it is being stabilized by these three electron donating groups connected to it. So if it is a tertiary one, what is a tertiary one? The carbon is connected to three other carbons. That's a tertiary one. If the carbocation is the tertiary carbocation, then it is going to be more stable than, say, this type of carbocation where you have these hydrogen groups and they simply cannot shift this, cannot do this type of thing over here. So this is not going to be stabilized by the groups connected to it. So this is not stable. It won't exist. It will exist for a very small time, you can say. This is very stable. So if a reaction is having a step which involves the formation of carbocation, then you can say that it will follow this order. It's like, you can say the rate of the reaction will be maximum for a tertiary reactant, then for a secondary one, then for a primary one, and then for a super primary. You can call this type of carbocation is a super primary one. So this is the rate of reaction. It's going to increase this side. If it is a tertiary, it is better for it because it is going to be more stable. For secondary, it is in between, you can say. For primary, there's very less probability that a primary carbo alkyl halide is going to show this kind of mechanism, SN1. It won't show. It will in fact prefer SN2, as you have seen there. The parameter in SN2 is the steric hindrance. So it needs a less complicated, simple structure for the reaction to go or to follow that SN2 mechanism. So this primary or super primary will follow SN2, while a tertiary one will follow SN1. If you know some basics of chemical kinetics, then you would know that if a reaction is taking place in multiple steps, then there is a thing called as rate determining step. And you can observe that the first step, which is the formation of carbocation, is a slow one, while the second one is pretty easy and very fast one. And you can call this one as a rate determining step because they always choose this slower step as the rate determining step. And what is that one? What is the first step? Step one. You can go over here, like I think this one. Yeah, this is our first step here, where only one reactant is taking part, and that's why this is a unimolecular reaction, or you can say that the rate of the reaction depends only on one of the reactants. That's why it is called as a unimolecular reaction. Unimolecular. That's why SN1. And in SN2, since it is a one-step reaction and the rate depends on both the reactants, it is called as a bimolecular reaction. So it is simply related to chemical kinetics, you can say. We'll talk a little bit about the solvents which are used in SN2 and SN1 reactions. So you can see fundamentally there are broadly two types of solvents. One is polar solvent and the other one is non-polar solvent, and we are interested in these polar solvents now. Both in both of these type of reactions we use polar solvents. So in polar there is further classification as protic or aprotic. The meaning is very simple. If you have a solvent like water, say, which is H2O, and it can easily give this hydrogen from it as the bond is polar bond, or it is H donor, then it is a proton donor or a protic solvent. And if it is a polar solvent but it won't leave that hydrogen easily, it's a aprotic solvent. And we'll see which type of solvents are used in which reactions. So the logic is very easy over here. When you use a protic solvent, then it's going to give those H positive ions. And if you are talking about the SN, I'll just write it. If you are talking about the SN2 reactions, and you consider that nucleophile, say OH, is present, which is going to attack our substrate. And what if there are many H positive present due to the solvent, or if the solvent was protic solvent, then it will leave many of these hydrogen positive ions into it. And what will happen then? This OH will no more be interested in going to that C, as you have seen in SN2 mechanism. It won't be interested in reaching to that C because it is now easily getting this hydrogen, so it is going to get uh, it's going to uh, get combined with this hydrogen easily. You can say this, all these nucleophiles will get this positive charge easily. They won't approach this substrate then. So it is not advised to use a polar protic solvent in SN2 mechanism. So they use a polar solvent, but a aprotic one like acetone. This is a polar aprotic solvent. So acetone is a typical example, which is a polar as well as a protic solvent. So if you see acetone being used, then it most probably will be a SN2 type of reaction. And if it is a polar protic solvent, then it is generally SN1 reaction, because in SN1 reaction, the first step involves the formation of carbocation. And if you can if you can see this step here, which is the first step, the formation of carbocation, you can say that the solvent will help in this is the solvent will help in this formation or the stability of carbocation, because if the solvent is polar, then it's going to stabilize these ions, this one and this one separately, and it will prevent them uh, in forming these, combining again and forming this part. Okay, so we need a polar protic solvent for SN1 and a polar aprotic solvent for SN2. That's it.